Okay, so in this video we are going to go through solutions, which is Unit 7. And it's important, the study of solutions is important because a lot of things that you use in your everyday life are solutions. And we're going to need to know some of the basic properties of solutions to understand some of the things that we go over in the next couple of units. So before we start, I want to go through the fact that a solution can be abbreviated SOLN. So if you see SOLN, it just means it's another way of writing solution. So a solution is defined as a homogeneous mixture. And we know that we learned back in Unit 2 that all matter can be split up into two big categories. It can be either a pure substance, which is an element or a compound, or it can be a mixture, which is two or more elements or compounds that are physically combined, two or more pure substances that are physically combined. Now, for mixtures, they can be heterogeneous or they can be homogeneous. A homogeneous mixture is a mixture that has a uniform composition at the molecular level. So that's what a solution is. It has a uniform composition at the molecular level. All solutions contain two parts. They contain a solute, which is the substance that's being dissolved, and a solvent, which is the substance that is doing the dissolving. Now, we tend to think about a solution as dissolving something that's solid in a liquid. So taking some salt or some sugar and mixing it with some water and making a solution. But you can actually make solutions of many, many different types. So for example, if you dissolve a gas in a gas, that would be our air that we breathe. Our air is just a solution of gases. If you dissolve a liquid in a liquid, that would be something like alcohol that you'd buy at the store, hydrogen peroxide that you buy at the store. They give you antifreeze, vodka, anything like that. You can dissolve a solid in a solid. Those are often called alloys, something like brass or stainless steel or there are other types of alloys, solids dissolved in solids. You can have a gas dissolved in a liquid. That would be like a carbonated soft drink. You can have a solid dissolved in a liquid. Those were the solutions I was talking about that tend to be most common, something like a sugar solution or most of the solutions that we would make in lab. And then you can also have a gas dissolved in a solid. So the point of this is I just want you to see that there are lots of different solutions that you can make. It doesn't just have to be a solid dissolved in a liquid. All right, so I want to go through some basic properties that all solutions have. And these are written on your definitions sheet. And so you can follow along, but you already have these written down for you if you're looking at the definitions sheet. So the first property is that the distribution of particles in a solution is uniform. Remember, the definition of a solution is a homogeneous mixture. It's a mixture with a uniform composition, and it's a uniform composition down to the molecular level. The second property is that the components do not separate upon standing. So once you make a solution, once you combine the solute and the solvent, they don't separate. They don't settle out. The particles do not settle out. A solution cannot be separated by filtration. So we had an example of this in lab. In lab, we separated a mixture of salt and sand. And the way that we did it was by adding water. And adding water made the salt dissolve in the water. We then passed it through a filter, and the sand stuck on the filter because the sand never dissolved in the water. But the salt that was dissolved in the water, the solution of salt water, went through the filter. So you can't separate a solution by trying to filter it. Also, for any given solute and solvent, it's possible to make solutions of a lot of different concentrations. Solutions are almost always transparent, meaning you can see through them. And a solution is a mixture. So even though it can't be separated by filtration, it can be separated by physical means. And again, you saw that in lab. I was talking about our salt solution, our salt water solution. We did separate that by boiling it. And boiling it made the water boil away. The water evaporated and boiled away, and we collected and masked that salt. So that it is possible to separate a solution by physical means. So one of the most common solvents is water. And I want to spend a few minutes talking about why water is such a good solvent. Because a lot of the solutions that we're going to talk about for the rest of this chapter are going to be solutions of something dissolved in water. So water is called the universal solvent. And the reason it's the universal solvent is because of its polarity. So by now you should know how to draw a water molecule. This will be, I drew it in the chapter, I think, on liquids. We've talked a lot about water this semester so far. So this is my attempt at sketching this using my cursor, which is not always easy. Then there are two lone pairs. So that is what a water molecule looks like. Now, way back in the chapter on molecules, on compounds, we said that the oxygen-hydrogen bond of water is polar. That means that the oxygen and hydrogen are not sharing the electrons equally. Hydrogen has a lower electronegativity than oxygen, so the oxygen actually has the electrons slightly closer to it. So because of that, we know that the oxygen will become slightly negative. This is very hard to draw. The oxygen is slightly negative, and the hydrogens are slightly positive. Furthermore, because of the shape of water, and if you look at the shape, there's this end of water is bent. This end is a negative end, and this end where the hydrogens are is a positive end. So we know that water is polar. So it's got that separation of charge. Now, the fact that it has that positive and negative end makes it good at pulling things out of a crystal. So again, if this is a crystal, take something like sodium chloride that has sodium ions, which would be the positives, and that has chloride ions, which would be the negatives. So if you look at this positive ion right here, it is attached to the negative oxygen. Or not attached, attracted to the negative oxygen. So eventually these water molecules are going to pull this positively charged sodium out of the crystal and are going to surround it. So the negative end of water is going to be surrounding that positively charged sodium. Now if you look at the other, I don't want to use green because this is green. Pink. If you look at the negative chloride, the positive end of water can attract that negative chloride and pull it out of the crystal. And eventually you'll have a negative chloride ion surrounded by the positive ends of all of these water molecules. So water is really good at pulling apart ionic substances. Now if we look at this in equation form in the next slide, we've talked about this before. We've said that any ionic substance, when it dissolves in water, breaks up into ions. And the reason that it does that is that those water molecules are pulling the ions out of the crystal and making the crystal structure break apart. So sodium chloride, when it dissolves in water, will split up into sodium ions and chloride ions. Once the ions are created, we say that they are hydrated, meaning they are surrounded, like we said before, by water molecules. That's what hydrated means. Now, the process by which this takes place is called dissociation. So rather than saying that ionic compounds split apart when they dissolve in water, we can also say that they dissociate when they dissolve in water. When that happens, they form a solution that can conduct electricity, which is called an electrolyte solution. So an electrolyte solution can conduct electricity. Now, why can it conduct electricity? Because it contains dissolved ions, which can carry a charge. So again, if you remember in the last slide, we looked at the dissolved ions. This would be a dissolved ion, and this would be a dissolved ion. These ions then can carry a charge. This diagram shows a couple of different solutions, and what you have is a light bulb that's got two electrodes, a positive and a negative. It would be hooked up to a battery, and when you complete the circuit, if the solution can conduct electricity, the light bulb will glow. So in this beaker, we have a strong electrolyte. Notice the light bulb is glowing brightly because you have negative ions and positive ions. This would be something like sodium chloride. In this beaker, notice that the light bulb is glowing, but it's not glowing very brightly. And that's because you have a couple of ions. Here's a positive and here's a negative. But mostly you have the molecules still being attached to one another. And then in this case, you don't have any ions, so the light bulb does not glow at all. So this would be considered an electrolyte solution because it can conduct electricity. This would be a strong electrolyte. This would be a non-electrolyte, something like sugar. And then the one in the middle would be a weak electrolyte. Okay, so what we're going to talk about next is factors that affect how much of a solute can be dissolved in a solvent. But before we do that, we need to talk about what is a saturated solution. So the definition of a saturated solution is that it contains the maximum amount of solute that will dissolve at a given temperature. So let's talk about how we would make a saturated solution. So to make a saturated solution, you would take a beaker of water, and we're going to make a saturated solution of sodium chloride. So you would add sodium chloride and you'd stir. Now, if all of the sodium chloride dissolved, notice it's all dissolved, you can't see it, that's not a saturated solution. That's an unsaturated solution. So you'd add more sodium chloride until you finally got to the point where you had some undissolved solute on the bottom. The solution that exists above that then is considered a saturated solution. So that's what a saturated solution is. Now, saturated is just a condition. It means it contains the maximum that can be dissolved. The amount then that makes it saturated is defined as solubility. So solubility is the amount of a solute that dissolves in a given quantity to produce a saturated solution. So the condition that exists, the solution here is saturated. The solubility of sodium chloride would be 36 grams. It It says right here, in 100 milliliters of water. So, solubility is different than saturated. So, we want to talk about what are some factors that affect solubility. And there are 3 of them that we're going to go over. First one is like dissolves like. The second one is temperature. And the third one is pressure. So, first of all, like dissolves like. Like dissolves like refers to chemical structure. And in general, the more similar two substances are, the more likely they will be to dissolve in one another. And by more similar, I mean the more similar their polarities are. So, polar substances will dissolve in polar solvents. Water is polar. That's why it's good at dissolving polar solutes. Ionic would be like an extreme case of polar, where you have a total separation of charges. So that's why water is good at dissolving excuse me, polar or ionic solutes. Nonpolar dissolves nonpolar. And there are lots and lots of practical examples of this. Things that dissolve in water generally because they are polar. Think of something like nail polish. Nail polish is not polar. If you want to take nail polish off of your fingernails, you don't use water because water won't dissolve the nail polish. You need to use something like acetone, which is the active ingredient of nail polish remover. Another common example would be vitamins. There are certain vitamins that you can take and really not an unlimited amount, but a large amount, and it's not going to harm you. The reason is that those vitamins are water soluble. So they dissolve in your blood, and then whatever your body needs, it uses. Whatever it can't use, it's excreted through your urinary system. And you have to consume them regularly because they dissolve and then they get excreted. Vitamins that are fat soluble are usually non-polar because fats are non-polar. So those are vitamins that will build up in your fat stores. Now your body's using them, so you do have to continue to take them, but if you take too many, they're not going to be excreted regularly, and they'll end up building up in your body's fatty tissues, and then sometimes they can cause problems. So that's why there are vitamins that it's okay to take a lot of, and vitamins that you need to really pay attention to how much you're taking. Same thing with other drugs, depending on whether they're water soluble or fat soluble. Okay, the second effect is temperature. And the one thing that you have to realize about temperature is that there's no formula that we can use to determine how temperature is going to affect solubility, because it really affects different substances differently. In general, the solubility of a solid is increased. So the solubility of a solid increases with an increase in temperature. Now, they don't all increase the same way though, and that's why I chose this diagram. So if you look at sodium chloride, which is table salt, table salt has a solubility of about 35 grams per 100 milliliters of water at 0 degrees Celsius. If you heat that up to boiling water, the solubility only increases by about 5 grams. So at 100 degrees Celsius, 40 grams of sodium chloride will dissolve. So it only goes up from 35 to 40. If you look at something like potassium nitrate, at 0 degrees, it has a solubility of about 15. And then by the time you get up to just above 70, its solubility has gone up to 150. So it is greatly affected by increasing the temperature. So in general, for salads, the temperature is as you increase the temperature, the solubility also increases. Oops, sorry. Trying to. Now, for gases, the opposite is true. So in general, the solubility of a gas decreases with an increase in temperature. And this can have some important practical applications. If I want you to pay attention to oxygen. So here's oxygen, it's the purple line on this graph. Animals that live in water, like fish and certain insects and crayfish and certain aquatic animals, rely on oxygen dissolved in the water to breathe. The amount of oxygen that's dissolved in the water depends on the temperature of the water. So you can see that the amount of oxygen dissolved goes down as temperature goes up. So that's why in the summer, if you have a shallow stream that's going to get pretty warm, you're not going to see very many things living in it because there's not going to be enough oxygen dissolved in the water for the fish to breathe. So some aquatic animals are just plain temperature sensitive, but a lot of times it has to do with the amount of oxygen that's dissolved. So to summarize, for solids, usually their solubility will increase with an increase in temperature, but for gases, the opposite is true. Their solubility decreases with an increase in temperature. For liquids, dissolved in liquids, it doesn't really have, temperature doesn't really play an effect. All right, the third factor that affects solubility is pressure. And pressure doesn't have much of an effect on the solubility of a liquid or a solid in a liquid. But it does have a great effect on the solubility of a gas in a liquid. So an increase in pressure increases the solubility of a gas in a liquid. And this is described by Henry's law, which is another gas law, and it says the amount of a gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. So the higher the pressure above the solution, the more gas will dissolve. So here's an example. We have a solution of a gas dissolved in water or some liquid at a certain pressure. If you increase the pressure by decreasing the volume, so here's the pressure is going up, there's going to be more gas particles present in the solution. Now, a common example of that would be a soft drink, which is why I chose this picture on the left-hand side. Soft drinks are bottled under pressure, meaning that the pressure in the can or in the bottle is much greater than atmospheric pressure. When you open that soft drink, then that releases the pressure. And so the bubbles of soft drink, of carbon dioxide, come to the surface and eventually escape, because carbon dioxide is not as soluble in water at atmospheric pressure as it is in the pressure at the pressure that it was bottled at. And so that's why soft drinks go flat. Now, if you want to keep it fresher a little bit longer, you can reseal it, and some pressure will build back up, and that'll prevent more from escaping. But that's a practical example of Henry's law. So those are the three factors that affect solution concentration. That affect solubility. Now I want to go through concentration. And the concentration of a solution can be measured in many different ways. The most common way in chemistry, and if we weren't online for the rest of the semester, I would tell you that you needed to memorize this, but the most common way is molarity. Molarity is extremely important. So you should have noticed in lab, whenever you saw labels on a liquid, like in our types of chemical reactions unit, or in one of the last labs that I did, we had to use 6-MHCl. Okay, that M stands for molarity. Molarity is defined as moles of solute per liter of solution. So 6-MHCl means 6 molar hydrochloric acid, or HCl, which means 6 moles of HCl per liter of solution. Most common way of measuring solution concentration, and we'll be talking about it often in the rest of the chapter. Another not so common but still important way is called molality, which is moles of solute per kilogram of solvent. And molality is important in several formulas, which we are not going to go into, but that's just another unit. Mass percent has some practical examples in everyday life. For instance, if you go to the grocery store and you buy 3%, or you buy a bottle of hydrogen peroxide, it's going to be 3%. That means it's got 3 grams of hydrogen peroxide per 100 grams of solution, because you multiply it by 100 to get a percent. So 3% would be 3 grams per 100 grams. If you buy a 60% alcohol solution, it's 60 grams per 100 grams of solution. And then I included parts per million. We'll never use parts per million, but it is something that you'll see occasionally. Many towns, I know the town I live in, is required to put out a water quality report every year. And it's a way of reporting things that are present in really small amounts. Like, take for instance arsenic. Arsenic is present naturally in some drinking water. The EPA said you can't exceed so many parts per million. So parts per million is a small unit because it's milligrams of solute per kilogram of solvent. So these vary by a factor of 10 to the 6th. And so it's a very, very small amount. So if you have something that's 2 parts per million, it means it's 2 milligrams per 1,000 grams of water, which is very, very, very small. It would be like saying 0.002 grams per 1,000 grams. So it's very small. The unit that you definitely need to know is molarity, and that's the unit that we're going to use for the rest of this this chapter, or the way that we're going to measure concentration in the rest of this chapter. Okay, pretty soon I will have you stop watching the PowerPoint and look at some problems, but I want to go through how we make a dilution. Many things that I would buy, or many things that you can buy, or come in a concentrated form. And then you have to dilute that by adding water. So making a dilution just means that you are adding more solvent to lower the concentration. So let's look at this slide up here. And this is a slide that I have drawn in class before. So let's say you wanted to make some sweet tea. And we took a cup of tea and we dissolved 2 sugar cubes in it. So the concentration of our sweet tea, and it's not really concentration, that's why I put it in quotes, it's not molarity or molality, but we're just going to say it's 2 cubes dissolved in 1 cup of tea, so that's a concentration of 2. I want to erase that because that didn't turn out very well. So let's say you take a sip and you decide that's too sweet. So you add more tea. So in a sense, you're diluting your solution. But you started out with 2 sugar cubes, and you still have 2 sugar cubes. You didn't do anything to the amount of sugar. Once your sugar's dissolved, it's not like you can make it less sweet by taking the sugar out. That would be hard. I mean, you could do that, but that would be hard. So if you want to make it less sweet, you just add more tea. So now the new concentration is now 2 cubes. So the 2 cubes stayed the same. That number didn't change. But the concentration changed because it was 2 cubes per 1 cup, and now it's 2 cubes per 2 cups. So it went from a concentration of 2 to a concentration of 1. And so that's what happens when you make a dilution. You're just adding solvent, but the amount of solute does not change, or the amount of solute, yes, does not change. So when you are making a dilution, you are adding more solvent, but the number of moles of solute is going to stay the same. So that's going to enable us to then come up with a formula that we can use that will make it easy to make dilutions. So this is the formula that we're going to use. M1 times V1 is equal to M2 times V2. So how do we get that? Well, we said that the number of moles stays the same. Remember in the previous example, I said you got your sugar cubes, you're just adding more tea, but the number of sugar, the amount of sugar is going to stay the same. So remember that molarity is defined as moles divided by liters. So if we want to solve this equation for moles, then we can multiply both sides by liters. So molarity is equal to moles times liters. That's how we get M1 times V1. And we use V volume instead of liters. So we've got molarity times volume, because molarity times volume is equal to moles. So we said the number of moles doesn't change, so the moles after the dilution is equal to the moles before. So if moles after is M2 times V2, that's going to be equal to moles before, which is molarity times V1. All right, so now is a good time to stop the PowerPoint and go through and look at the other recording that I made, which is how to do the how to calculate molarity and how to make dilutions. Okay, so you should have stopped and gone and watched the in-class exercises, how to do the in-class exercises. And now I want to go through and talk about colligative properties. Colligative properties describe how adding a solute affect the properties of the pure solvent. And like we have in the past, we're going to focus mostly on water. So how does adding something to water affect the properties of water? That's what we mean by colligative properties. And we're going to look at 4 different colligative properties. We're going to look at vapor pressure lowering, boiling point elevation, freezing point depression, and then something called osmotic pressure. Now, in real life, colligative properties can be used to determine the molar mass of a substance, but we won't be going over any problems like that. We're just going to look at if I add some salt or something to water, what happens to the boiling point of water, what happens to the freezing point of water, and what happens to the vapor pressure of water. Now, colligative properties don't necessarily depend on what you're adding. It depends on the number of particles that that substance is going to create in solution. So the more particles that can be created, the more of an effect that substance is going to have. So I want to compare two different salts and how they'll affect the water. So we're going to compare sodium chloride to magnesium chloride. So sodium chloride, we just said, when it's dissolved in water, breaks up into sodium ions and chloride ions. And so if you start out with 1 mole of sodium chloride, 1 mole of sodium chloride will produce 1 mole of sodium and 1 mole of chloride. So 1 plus 1 is 2 moles of ions. So 1 mole of sodium chloride will produce 2 moles of ions. Now if you compare that to magnesium chloride, okay, magnesium chloride is going to split up into magnesium ions, and it's going to split up into chloride ions. Now this 2 right here means that you have 2 chloride ions for every 1 magnesium. So 1 mole of magnesium chloride will split up into 1 mole of magnesium ions and 2 moles of chloride ions. So you're going to get 3 moles of ions. So this substance produces 2 moles of ions, and this substance produces 3 moles of ions. So because magnesium chloride produces more ions, magnesium chloride will have the greater effect because it produces more ions when it's dissolved in water. Now, be careful when you're looking at a substance and it's got a polyatomic ion. Remember, polyatomic ions stay together. So if it would be something like MgNO3 the NO3 is going to stay as NO3 when it dissolves in water. Those ions stay together, even if it's a polyatomic ion. All right, so now let's look at some of the colligative properties. So the first thing I want to look at is something called vapor pressure lowering. So what that means is that if you add a solute, it's going to lower the vapor pressure of the pure solvent. So adding something to water lowers the vapor pressure of the water. So in this diagram, we've got pure solvent. And in the last unit on states of matter, we talked about how all substances will evaporate. They can take in heat from the surroundings and they evaporate. If they're evaporating in a closed container, they create a vapor pressure because you've got collisions of the particles with the walls of the container. And so in this vessel, the vapor pressure is 3. Now, adding a solute takes up some of the space. So not as many of these green solvent particles can come to the surface and evaporate. It kind of blocks some of the solvent particles from evaporating. So you can see that the pressure of the solution is lower. So the pressure of the solution is lower because of adding the solute. So adding a solute is going to lower the vapor pressure of the solution. So then anything that depends on vapor pressure is going to also be affected. And the one thing that depends on vapor pressure is boiling point. We said that the boiling point is defined as the temperature at which the vapor pressure equals atmospheric pressure. So adding a solute is going to raise the boiling point of a pure solvent. So adding something to water is going to make it boil at a higher temperature. Why? Because it lowers the vapor pressure. So now water is going to need even more energy so that its vapor pressure can be equal to atmospheric pressure. So if we would do this in lab, and I do plan on doing a demonstration of this, if I add something to my water, it should boil at a higher temperature. Another thing is freezing point depression. Adding a solute lowers the freezing point of the pure solvent, and this has some practical effects in the winter. We live in a climate where it gets cold in the winter. We have snow and ice, and you know that often the roads will be salted when it gets snowy. Now, the salt itself does not melt the ice. The ice on the roads is melted from either energy from the sun or friction from car tires running over it. What happens though is that the salt then that's added makes a solution with the water as the ice melts, and that solution is going to refreeze at a lower temperature. So instead of refreezing at 32 degrees Fahrenheit, which is the freezing point of water, maybe it'll freeze at 10 degrees Fahrenheit or even lower. And that's why when you get below a certain temperature, adding salt is not as effective, because there are limitations to how much lower the freezing point can be depressed. So that's how adding something affects the properties of the pure solvent. It's going to raise the boiling point and it's going to lower the freezing point. And again, the more particles that it breaks up into, the more of an effect you're going to have. So I want to go back a few slides. So sodium chloride, if you compared sodium chloride and magnesium chloride will elevate the boiling point and lower the freezing point of water more than sodium chloride will, because magnesium chloride breaks up into more ions. All right, so the last colligative property that I want to go over is called osmotic pressure. And osmotic pressure comes from a property called osmosis. Osmosis is the movement of a pure solvent through a membrane. So if you look at the diagram on the right, the solvent particles are blue and the solute particles are orange. And notice that this is called a semi or partially permeable membrane, which only is allowing the blue particles to go through. It's not allowing the solute particles to go through. So the solute or the solvent particles kind of want to try to equal out the concentration. So what's going to happen is they're going to move through, going from less to more concentrated faster than they're going to go in the opposite way. But eventually you'll get to a point where the movement is the same. So if you would look at a U-shaped tube and you put a solution on one side and pure solvent like water on the other, again, the water wants to try to even out the concentration. So it's going to flow from pure water into the glucose solution, and it's going to make it more dilute. Now it's still going both ways, but initially it's going to flow in more, going from left to right, going from pure solvent into solution. Now, what's going to stop it from going all the way up or from continuing to go up? Well, what's going to stop it is the pressure of the atmosphere pressing down on this tube. And so eventually then it's not going to be able to move up any farther. And the number of solute or solvent particles going this way is going to equal the number of solute particles going in the opposite direction. This pressure difference is called osmotic pressure. Now, if you apply pressure, what you've done is used a technique called reverse osmosis. And what you do then is reverse the process. So reverse osmosis is a way of purifying a solution. So that's osmotic pressure. And osmotic pressure is especially good at, or let me rephrase that. Osmotic pressure is used in a lab situation for determining the molecular weight, because a very, very small amount of a protein can create a pretty high osmotic pressure. So the last thing that we're going to do in this chapter, and this is only a couple of slides, is we're going to look at some mixtures that look like solutions but aren't really true solutions. Because remember, a solution is something that's homogeneous at the molecular level. And there are mixtures that exist that are not homogeneous at the molecular level, but to the eye level, they look like solutions. And they are called colloids. So a colloid is defined as a mixture that's not a true solution at the molecular level. The reason it's not a true solution is because of the size of the particles. So in a solution, the particles are usually less than 1 nanometer. And so at the molecular level, you have a true mixture. They're equally or evenly mixed. In a colloid, the particle size can be from 1 nanometer to 1,000 nanometers. And then there's another type of mixture called a suspension, where the particle size is greater than 1,000 nanometers. Now, in a colloid, the particles still usually stay mixed together. In a suspension, in order to keep them mixed, you have to shake up the suspension. And immediately after you stop shaking, the particles are too large and they fall out. So an example of that would be, think of oil and water salad dressing, like Italian dressing. You have an oil layer and a water layer. If you shake it up, you can suspend the oil in the water briefly, but once you stop shaking, the oil separates from the water. Most, like a child's antibiotic or children's Motrin, or those are usually suspensions. Antibiotic is not very soluble in water, most antibiotics. So what they'll do is it'll be ground up into a very, very fine powder, like baby powder fine. And then the pharmacist will mix it with water. But when you get that bottle of liquid antibiotic, it will say shake well before using, because you're not really creating a solution, you're creating a suspension where the particles are too big. So let's go back to colloids though, because colloids a lot of times look like solutions. And colloids are pretty common. So instead of having a solute in a solvent, we would have the dispersed phase, which would be like the solute. I'll write that down, maybe. So this would be like the solute. And then the dispersion medium would be like the solvent. So this would be like the solute, this would be like the solvent. So you can have a liquid dispersed in a gas, that's called an aerosol. So an example of that is a fog, clouds, mist. You can have a solid dispersed in a gas, that's also an aerosol. So when you see smoke from a fire, that's because the particles of soot are dispersed throughout the air. You can have a gas dissolved in a liquid, that's called a foam. Shaving cream would be an example, whipped cream. You can have a liquid dissolved in a liquid, that's called an emulsion. You can have a solid dispersed in a liquid, that's called a sol. A gas dispersed in a liquid, that's called a foam. You can have a liquid dispersed in a solid, that's called a gel, like Jello. Or you can have a solid dispersed in a solid. So those are all types of colloids, and these are all common things that they don't settle out when you upon standing, but they're not true solutions at the molecular level. So how can you tell then whether something is a colloid or a solution? Well, solutions, or colloids I mean, exhibit something called the Tyndall effect. The Tyndall effect is the ability of a colloid to scatter particles of visible light. So, to observe the Tyndall effect, you would take a laser and you would shine it through a beaker. So this is looking down on these beakers. So the beaker on the right contains a solution. And notice that as the laser is pointed and goes through the solution, you can't see the laser. The beaker on the left is a colloid. The particles, or the light, is visible going through the colloid. That's the Tyndall effect. So why don't we see the light in the solution? Because the particles are too small. In a colloid, the particles, the dissolved particles, are big enough to scatter visible light. So this ends the unit on solutions. You should have also watched the video on how to do the problems, the solution problems, and you should be ready to take your solutions quiz.